All right, we are on page 5 in our packet. This is multiple representations of relations and functions. So remember, multiple means many representations of relations and functions. So these are all the ways that we can see relations and functions in math. So our TEK is still A12A like it was the other day. It says decide whether relations represented verbally, tabulary, I don't even know how to spell that word, graphically and symbolically define a function. Our bold statement says, similar to a relation, a function can be represented in multiple ways, like a graph, a mapping diagram, table, equation, a set of ordered pairs, and a verbal description. So we have scenario 1, and here's our verbal description. So write this down in your packet. This is a verbal description right here. It says you are running at a rate of 7 miles an hour. Record your mileage for the first 5 hours. So we are running 7 miles per hour. Per means we're going to multiply 7 and hours. Okay? So let's think about it logically. We have a set of ordered pairs in brackets. This is what we call a bracket with commas between each ordered pair. So let's think about for the first 5 hours. So we have hour 1. After 1 hour, we would have ran 7 miles because it's 7 miles per 1 hour. So 7 times 1 is 7. So that is our first ordered pair. X equals hours. Write this down. And Y would equal miles. Okay, now that's a little bit easier to see. Okay, now we're going to do 2 hours. 2 hours would yield 14 miles total. 3 hours would be 21 miles. 4 hours would be 28 miles. And 5 hours would be 35 miles. And then close your relation in with a bracket. Okay, so we have our 5 ordered pairs, and we're going to take these 5 ordered pairs and place them in a table. So we have our relation written as ordered pairs. So everybody write this right here. All right, and now we're going to see it as a table. Okay, so all of our X's is 1 hour, 2 hours, 3, 4, and 5. So your hours can go horizontally across the table. And if it's a vertical table, they would be going down. 1, 2, 3, 4, 5. So this is the hours. The input is the X. The output is the Y. Okay, let's answer our miles, which is 7 miles for hour 1, 14 miles for hour 2, 21 miles for hour 3, 28 miles for hour 4, 35 miles for hour 5. Now we can graph. We've got hours. We've got miles. Okay, so 1 hour is 7 miles. 2 is 14, 3 is 21, 4 is 28, and there's not enough graph to graph 5. And then obviously, if we ran 0 hours or whatever, we'd have 0 miles. And since we are running, in order to get to 7 miles, we would have to run between that. So connecting these does make sense. In a mapping diagram, we're going to call this our X oval. It's always first. And the second oval is the Y oval. And we're going to put our X values. Now, most of the time when you work with mapping diagrams, the arrows don't just go straight across, but because we're putting our numbers in numerical order, it's going to go straight across. But your normal mapping diagram does not go straight across. But because this is a linear relationship and we're doing the first 5 values of X and Y, that's why they're going straight across. So this is how we would map my X values, my inputs, to my Y values, my outputs. Again, this is called a mapping diagram. In the equation, the total number of miles, which is Y, is represented by 7 miles an hour times hours. And that's how we find the equation. Okay, let's read 3 problems from past STAR test and how they showcase functions. So this question says, which table shows Y as a function of X? So I'm going to circle Y as a function of X. So only one table is a function here. Which one? So let's think about what the definition of a function is in relationship to a table. So if you scroll back up or flip your packet back to page 3, it'll show you a table that is a function and a table that's not. If you can remember from your lesson before this, you really focus on the X of your table. So we're looking at the X's. And we want the table that is a function. In order to be a function, X can't repeat. X can't repeat. If it repeats, not a function. So F has 4 numbers that are the same. That's repeating. It's not F. H has a 1, a 3, a 7, and a 12. Each X is assigned exactly 1 Y. So 1, 4, 3, 4, 7, 4. Y repeating doesn't matter. Therefore, our answer is H. X does not repeat. The other table, there's 2 -1s, and here there's 2 zeros. You can't have the same X with different Y's. Let's look at 38. 38 is still talking about function, but check it out. Now they say which one does not show Y as a function of X. So now we have to switch the brain. Which, come on now, table is not a function. So 3 of these are functions. 1 is not a function. Okay, if something is not a function, X repeats when it's not a function. So we're looking for a table with the X repeating itself. Here we go. 1/10, 1/8, 1/5, 1/4, 1/2. That is a function. We're looking for what is not. 14, 15, 16, 17, 18. None of those X's repeat. So all of these are functions. Negative 0.2, 0.6, 1.3, 1.0, negative 0.2. All right. This one is not a function because X repeats. So we want to bubble in H. The last question. Now these are all STAR questions. So some freshman has taken the STAR test and has had to answer this question. Which table represents Y as a function of X? All this means is which table is a function. All right. Which table is a function? So 5 and negative 5 and negative 5 repeat. This is not a function. Negative 3 and negative 3 repeat. This is not a function. 6 and negative 6. 8 and negative 8. Ooh, X doesn't repeat. This is our winner. 2, 2, 2, 2, 2. X repeats. This is also not a function. So we're looking for the one that is a function. So when it is, the X will be different numbers. Remember on my notes, I say that each X, which we call input, has exactly one Y, which is the output. Okay, all right, let's take a look at the next page. This is how you say this title: discrete versus continuous functions. Discrete versus continuous. It's kind of like black versus white. Black and white are completely different colors. One's dark, one's light. Discrete and continuous functions look completely different, like night and day. So let's read the Texas TEK. It's different than the other 2 days that we've read the TEKs. We will determine the domain and the range. Coach, we haven't heard those words before. Now you have. We're going to determine the domain and range of a linear function in mathematical problems. We're going to determine a reasonable domain and range for real world situations. So both cases, you're learning domain and range. And the next comment says, both continuous and discrete, and represent domain and range using an inequality. So the good thing is, we just got done with inequalities, so they're fresh on our mind. We're going to be using inequalities when we write the domain and range of discrete and continuous graphs and verbal descriptions. So let's take a look at the types of functions. So I have wrote the word discrete. Go ahead and put a box around it and read the definition of discrete. The easiest definition: points are not connected. That's the most basic, boring definition. Discrete is disconnected points, not connected. Random points scattered on a graph. Discrete. What are discrete things in the real world? I'm looking right here. Things that can be counted are discrete. So looking in my kitchen right now, I can count the spoons, the forks, and the knives in the drawer. That's discrete, and I can graph. The forks, there's 21 forks. Spoons, there's 18 spoons. Knives, there are 30 knives. I can graph ordered pairs on a graph. Discrete things are people, number of books in a library, number of slices in a pizza. Discrete things are things that can be counted. Okay? So how many students are in the class today? I can physically count you. That's a discrete data. How many pairs of shoes do you have at your house? You can physically count. I have 5 pairs of shoes in my closet. I have 2 pairs of shoes in the garage. I have 2 pairs of shoes in the backyard because I mow the yard in these old shoes. I have flip-flops. Like, that's physically counting shoes. That's a discrete data. Channels on YouTube, discrete. I can count channels on YouTube. Number of series in Netflix. I can count the series in Netflix. I can graph that. The drama, there's 25,000 drama series in Netflix, whatever. You get what I'm saying. So discrete, I'm going to write it again. Discrete data can be counted. That is what it can be. And remember, when we graph it, it's random points. Now let's look at the other one, continuous. Continuous data. Continuous data, the most boring definition is unbroken lines or curves. Unbroken, connected, continuous means connect the points together. Continuous is connected. Discrete is disconnected. Okay, I'm hoping you will find these alliterations easy to remember which one's which. Continuous, connected. Discrete, disconnected. Okay, now what are continuous data? What's continuous data? Anything that can be measured is continuous data. I can measure time. I can measure height. I can measure someone's weight. I can measure the distance from here to there. I can measure the distance at a cross-country meet when little runner A and little runner B run the course. I can graph that. And the graph will be smooth and connected lines or curves. So remember, we're talking about continuous. Continuous data can be measured, and it's going to involve height, time, weight, distance, not counting, because that's discrete. All right, let's see. Number 1 says classify the following functions, either discrete or continuous. So I'm looking at number 1. I noticed that these are ordered pairs. Ordered pairs, if I was to graph these 4 points, all I would do is graph 4 points. I would have 4 points on a graph, and points on a graph are discrete. Why? Because they're not connected points. They're just 4 points on a graph. These are just 4 points on a graph. So number 1 is discrete. Number 2 is an equation. Now I can graph this equation, y equals 2x plus 5. Y equals 2x plus 5. I see that this is a smooth curve or connected straight line. And in this case, it's a line. This is a connected line. So the equation is a line, and a line is continuous. Number 3, I can see with my eyes that is a connected line or curve. So this is what class? Smooth and connected lines and curves are continuous. And number 4, we have a mapping diagram. Mapping diagrams, if I was to graph this, I would graph x is -1, y is 5. X is 0, y is 3. X is 1, y is 5. X is 2, y is 11. X is 3, y is 21. These are points on a graph. Points on a graph are discrete data because it's a mapping diagram. And a mapping diagram is made of ordered pairs. A mapping diagram is made of ordered pairs that are connected by an arrow. So you know which pair, which number goes with which number. Remember, here's my X. X is on the left side, Y is on the right side. Okay, we're almost done. We're just going to read through some new vocabulary. So far our new vocabulary is discrete and continuous data and now we have independent and dependent variable notes. So let's just read what an independent variables represent function inputs. Remember, inputs are x's. And independent variables are the ones we can freely manipulate by plugging in any input value. In most math problems, we think of what letter? X as the independent variable. Since it's the one we usually change, we usually plot the independent variable on the horizontal axis. So here's our graph. And we call this the independent axis, which we know is X. Okay, independent variable is your X. So the opposite of that would be your dependent variable. And dependent variables are your Y. Dependent variables are determined by the independent variable. In most math problems, we think of Y as the dependent variable, and we write that on the vertical axis, the Y-axis. So now I'm going to write dependent. Okay, so here's some other words you may hear. For independent variable, I for independent, V for variable, IV, independent variable. You might hear the words exposure variable, probably not much. Control variable, a little bit. Explanatory variable, never called it that. Manipulated variable, that makes sense. The dependent variable, DV, also called the outcome variable. Hey, what did you get as your answer? What's the outcome? That's the Y variable. So these are called Y's, these are the X's. Controlled variable. So we have control variable and the controlled variable. It's the explained variable, it's the response variable. Guys, we really will just stick to the word dependent and the word independent. Do not stress about these other words. This is just a explanation, if you will. Okay, how do you determine which variable is independent and which is dependent? Good question. The change in the dependent variable depends on the change in the independent variable. Example, the battery life remaining on your iPhone is based on the amount of time you spend using it. So the battery life remaining on your iPhone is based on, another way to say is based on is depends on the amount of time you spend using it. So which variable do we control? Do we control the battery life remaining on our iPhone? Or do we control the amount of time we spend using our phone? Which one do we control and which one is the controlled? So, which one needs to come first? Time spent using the phone comes first. As a result, your battery starts to get weaker or it starts to lose power. So, this would be the independent and this would be the dependent variable. There you go. Now in your homework, there are only 10. You're going to write, okay, the minutes I use my cell phone bill, which one do I have control over? Do I have control over the bill or do I have control over the minutes that I use? Yes, I have control over the bill. So this is going to be independent. The result, the company is going to say, hey, we're going to charge you 25 cents a minute. Well, the company controls the cost, and then however long I talk on the phone is going to start racking up, and then that's the result of my phone bill. So this is going to be dependent. Okay, so now you need to decide, is this measurable or is this counting? Okay, is this measurable or is this counting? So the question is, can you be on the phone for 1 minute? Correct. What about 1.2 minutes? Yes. How about 1.3 minutes? Sure. You can be on the phone fractions amount of time, or you can just, as soon as it hits 5 minutes, you're off the phone. That's not realistic. So this would be an example of continuous, because I can measure how long I'm on the phone. Time is measurable because time is measurable. So this is just me modeling how you're going to do this homework. So I've done the first one for you. Ask yourself, which one needs to come first? Which one do you control? Which one is the result? I can control how much I'm on the phone. As a result of me being on the phone, my bill comes in the mail. However much the bill is, I had control over it. All right, thanks for sticking with it. Please get your homework done. Have a great night. It's 10:30. I'm actually going to bed early.